In this lesson, we're going to look at a couple more ways to test to see if a series converges or not. So remember, a series like the series 1 over n from 1 to infinity is a summation. So this represents 1 over 1 plus 1 over 2 plus 1 over 3, so on and so forth, all the way to infinity. So it's an infinite series. Okay, so what we want to do is we want to think about this. We want to know if that series, that summation will actually converge on a number. And we've seen some examples of how it does sometimes and other times it doesn't. Well, if we were to go to a graph, let's say, all right, and let's call this n, and let's call this f of n, and we're going to consider the function f of n equals 1 over n. Well, if this was 1, all right, so we have the value 1 over 1, and then we have, so if this is 1 and this is 2, so on and so forth. So then we have 1/2, and we have 1/3, and we have 1/4, 1/5, 1/6. Okay, and in fact, I'll draw some lines here, okay? So the length of these lines are 1. The length of this line is 1/2. The length of this line is 1/3, 1/4, 1/5, 1/6. Okay? So this series represents the sum of each of these lines, the lengths of these lines. Okay? So what we want to do is we want to say, well, that can be a little hard to handle, but we have this tool called integrals. And if we think about the integral 1 over x, okay, so if we think of the continuous function, f of x equals 1 over x, okay, and let's say we want to find the area under this curve from 1 to infinity. So that's something we've worked with before. So if we wanted to find the area, how do we find the area of a curve? Well, that is an integral. So we can do an integral from 1 to infinity of 1 over x dx. All right? So this 1 over x is a continuous function, whereas the sequence of a sub n equal to 1 over n. So that sequence is discrete. So these values only occur at 1, 2, 3, 4, 5, so on and so forth. Okay? So we can compare the continuous version of this, which is all of this shaded area. So though, what we're going to say is if we know that this converges, then, meaning all of this converges, then the discrete sums of 1 over 1, 1 plus 1/2 plus 1/3 plus 1/4, that also will converge. Make sense? So if the shaded area goes to something, meaning it kind of closes off fast enough and that it has a sum, then the values of the blue lines there will converge to something. They won't be the same things, but they will converge. Okay? The opposite of that is also true. If the integral diverges, this improper integral here diverges, then the summation of the series will also diverge. And that is basically what we call the integral test. All right? So here's how the integral test works. If we have a function f, and that function is positive, continuous, and decreasing, all those things have to be true, and we've got a sub n is equal to some function of n. Okay, so a sub n is a function of n. Then we can compare it to this integral here. And either this integral and the series will both converge or both diverge. So in other words, we can look at the integral. If we know the integral converges, then the series does. If the integral diverges, then the series will diverge. Okay? So the key here is we need to make sure that it's positive, continuous, and decreasing first. Okay? If that's true, then we can use the integral test. If it's not true, we've got to do something else. Okay? So these are what we call the three hypotheses of the integral test. So when using the integral test, we must first verify whether the three hypotheses are true. And if that's the case, then we can evaluate the improper integral and decide whether that converges or diverges. So let's give it a try. So here we have the summation of n over n plus 1. And if we think of that as a continuous function here, we've got x over x squared plus 1. So those are comparable. Let's ask ourselves this: is f of x always positive for values of x that's greater than or equal to 1? Notice this n starts at 1, so we're considering an x that starts at 1. And yeah, if x is positive, the top will be positive, the bottom will be positive, the whole thing is positive. So this is true, yes. Is it continuous for all values greater than 1? Well, is there any value that will make the denominator 0? No, there is no value. So yes, it will be continuous. It's continuous for all real numbers, in fact. And lastly, is it decreasing for x is greater than 1? Well, we can justify this by finding the derivative. So let's go ahead and do that. F prime of x is the derivative of, this is the quotient rule. So the derivative of the top is 1 times x squared plus 1 minus the top times the derivative of the bottom, all over the bottom squared. Now we need to ask ourselves, is this positive or negative? Actually, let's clean it up a little bit first. So let's clean up the top. That's x squared. Looks like x squared minus 2x squared. See that? So x squared minus 2x squared will be negative x squared, actually, right? So negative x squared and plus 1 all over x squared plus 1 squared. Now, all we need to decide is that for x values greater than 1, will this be positive or negative? Well, when you pick a number that's 1 here, this will be 0. Okay, so and then if you pick something bigger than 1, anything bigger than 1 like 2 squared or 3 squared or 4 squared, if I have 2 squared, I'll have negative 4 plus 1. This will be a negative on top. And notice the bottom is always positive. Okay, so the top here will be either 0 when x is 1, or it'll be negative when x is bigger than 1. So this is always going to be less than 0 for x that is greater than or equal to 1. We should, I guess, say less than or equal to 0. So yes, this is always decreasing, or really it's non-increasing. Well, we can be more specific. We can say this is decreasing because it's going to always be negative, except for at that moment when x is 1. Okay, so, all right. So now, if they're all true, so yes, 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 we've shown that. And by the way, to show that, you don't need to do much more than this. You just stated the fact. The reader can reconfirm it for themselves, but you showed that you did confirm that for x greater than or equal to 1. Now, so let's find the improper integral here. So we're going to do the integral from 1 to infinity of x over x squared plus 1 dx. So this is the limit as b goes to infinity from 1 to b of x over x squared plus 1. So we've got to do it as a limit, remember. So we can do some little u substitution, let u equal x squared plus 1. So du is 2x. So I wish I had a 2x. Well, let's just put a 2 there. And I could do that as long as I multiply by a half also. So now, yep, we've got du right there. And we've got u. This is just 1 over u, also known as, let's pull the 1/2 out of the limit. You can do that because 1/2 doesn't have anything to do with b. So this is from 1 to b, and this is 1 over u du. All right. And since we did a conversion to u's here, a little reminder, we need to convert these to u's. So when you plug 1 into x squared here, u becomes 2. So we should change this. We need to make this u equals 2. Okay. And this is u equals b squared plus 1. Okay. But b squared plus 1 is still going to infinity as well, right? So the top we'll just leave as b because it's going to 0. Or infinity, sorry. All right, so if we integrate this, this is 1/2. Limit as b goes to infinity of the natural log of u, and this is from u equals 2 to infinity, or 2 to b. Okay, so as b goes to infinity, that's infinity there. So we end up with this 1/2 limit as b goes to infinity of the natural log of b minus natural log of 2. Now, what happens here? Well, as b goes to infinity, the natural log of b is also going to infinity. And this is just the natural log of 2. So, does this converge? Nope. It diverges. So if the function diverges, that means the series will also diverge. Okay? So the integral diverges, therefore the summation 1 to infinity of n over n squared plus 1 also diverges. All right, let's try another one. You may want to pause it and try the integral test on this. So let's look at the function here, f of x. F of x is 1 over x squared plus 1. And we got to ask ourselves, is this always positive for x greater than or equal to 1? And yes, it is. Okay, so it's always positive. Is it continuous? On 1 to infinity, all right? And yeah, it is, all right? So there's actually nothing that makes the bottom 0, so it is continuous. Yes. And last but not least, is it always decreasing? Well, the top's going to stay the same, and as this becomes 1, 2, 3, 4, 5, the bottom's getting bigger and bigger and bigger, never going to turn around. So yes, it is. Okay, you don't need to show much more than that, all right? But yes, we've got positive, continuous, and decreasing. You can just write it is positive, continuous, and decreasing. All right, let's find the integral here. All right, so the integral of 1 over 1 plus x squared dx. And we're going from 1 to infinity here. So we need to write this as a limit. So this is a limit. Let me just rewrite this here. So we'll just rewrite this as 1 to b is the limit as b goes to infinity. Okay, so do you recognize this? 1 over 1 plus x squared. I think that is an inverse trig function. Which one is it? It's arctangent. So this is the arctan of x from 1 to b. and the limit of that. Okay. And that is going to be the limit as b goes to infinity of arctan b minus arctan of 1. All right, so, well, what is the tangent, the arctangent, as b approaches infinity? Well, here we got to ask ourselves what's going on with arctangent. Okay, if you remember the graph of, let's think about some graphs here, because graphs give us a picture that tell us a lot. So y equals tan x. Okay, so we know what that looks like, hopefully. Tangent of 0 is 0. Remember, tangent is sine over cosine. Okay, so at 0, our tangent is 0, because it's 0 over 1 on the unit circle. And then as we get close to pi over 2, so pi over 2, at pi over 2, cosine is 0. So at pi over 2, it's undefined. Okay, and so this goes up like so, and we have an asymptote. And then it comes down at negative pi over 2, it's undefined also. Okay, well, the graph of y equals arctan of x is the inverse of this. So arctangent of x takes this and reverses it, and it looks like this. So as x goes to infinity here, the biggest that I can get is pi over 2, because there is no value that will get to pi over 2. You can't have an inverse tangent of pi over 2 because pi over 2 is undefined. So the limit as b goes to infinity is going to be pi over 2. And the arctangent of 1 we know is pi over 4, right? You know that? 45 degrees. Okay. And when you take pi over 2 minus pi over 4, that is pi over 4. Okay. But all that really matters to us is that this has a limit. And so this, since it has a limit, this function converges, or this series converges. So the integral converges. So the series 1 over n squared plus 1 converges by the integral test. Okay? So the fact that it goes to a finite numbers means that this converges. Therefore, that series will converge.